Welcome to our discussion on the arrangement of electrons in atoms. This discussion arises because of Rutherford's model of the atom. Remember, when we talked about our first three scientists, J.J. Thomson did the cathode ray tube experiment and discovered that electrons were negatively charged and that they had mass. And then Rutherford did the gold foil experiment and he discovered that the nucleus was really small. It was in the center of the atom. It was positively charged, and since it was located in the center of the atom, most of the atom had to be empty space. Okay? Well, Rutherford's model of the atom only talked about the nucleus. It had nothing to do with the electrons and didn't say where they were at all. So we're going to talk about where those electrons are. In order to talk about where those electrons are, we have to go through a discussion of wave-particle duality. I'll talk about what that is in just a second, and a description of light, because that's how our scientist Niels Bohr proved where the electrons are in an atom. So we're going to have to go through that first. Okay, wave-particle duality. The root word here of duality is dual, which means two states at once. Okay, so dual means to have both, alright? So that means that something is going to behave like a wave, and it's also going to behave like a particle at the same time. And that something that we're going to be talking about are all subatomic particles, namely a photon, which is going to be a particle of light. We'll talk about that in just a minute. Okay, we're going to talk about electromagnetism real quick. That's a force that causes an interaction between electrically charged particles. It's one of the four fundamental forces of physics, which you'll learn about when you take physics. Electricity and magnets are really the same thing. They're two halves of the same coin. And the electromagnetic force is what causes positive things to be attracted to negative things. Okay? And it's what causes the north pole of a magnet to be attracted to the south pole of another magnet. Alright. Let's talk about this wave description of light first. Okay, so light when it behaves like a wave. Okay? Visible light is what we call electromagnetic radiation, or an EM wave. Okay? So capital E, capital M stands for electromagnetic. Okay? And these electromagnetic waves are any of the types of radiation that you're normally comfortable hearing about. X-rays, gamma rays, radio waves, UV radiation, all that kind of stuff is electromagnetic. Okay? And it allows these things, these waves, to travel through space if they're in wave form. Okay? And since light can travel as a wave, we can actually calculate certain things about it because we have a wave equation. Alright? And that wave equation we get from physics, and we're going to use it here in chemistry just a little bit. Alright? Okay, so let's briefly talk about what each of these variables here stand for, okay? So v is the velocity or the speed of a wave, and you need to know that. It's the speed, how fast it's going, and the standard SI units are meters per second, okay? Then we've got f for frequency, and that's just how often a wave passes by a certain point, okay? And so that's going to be measured in hertz, which is the same thing as 1/seconds or inverse seconds. These two, all of these are the same, but remember from algebra class, if something is in the denominator, it's the same thing as having a negative exponent. I don't know if you remember that or not, but anyways, that's where it comes from. And then finally we've got lambda here, okay? Lambda is a Greek letter, okay, and it's going to mean wavelength for us. And since it's a wavelength, length is the key word there, distance is measured in meters, okay? So we're going to have a unit of meters there for our wavelength, and the one we're going to be most comfortable using for frequency is hertz. Okay, so let's see if we can't do a couple of wave problems. Okay, so here's a question. An ultraviolet light wave is used to kill bacteria. Coincidentally, this is how we sanitize your goggles after you've done a lab. We put it in that white cabinet in the back of the classroom, and it shines UV light down on it to kill all the bacteria. It has a frequency of 1.2 times 10 to the 15 hertz. Okay, remember this 1 over seconds here, that's the same thing as hertz. Okay, and it's asking us to find the wavelength. Okay, so we're going to write down our formula for the speed of a wave. So velocity is equal to frequency times wavelength, and they are asking us to find the wavelength. Okay, so let's do a little quick algebra review. You're going to circle the thing that you want, and then you leave it alone. Don't mess with it anymore. But you're going to look and see what's happening to it. And right now, it is being multiplied by frequency. So how do you undo multiplication? Division. So we're going to divide it by frequency. And whatever you do to one side of the equal sign, you have to do to the other. So we need to divide by frequency over here. So if we have frequency over frequency, you will remember, hopefully, that anything divided by itself is just 1. So we're going to cancel that out. That's like multiplying by the number 1 right here. Okay, and that doesn't change the problem at all. So we're going to say then that wavelength is equal to the velocity or speed of the wave divided by the frequency. Alright, cool. Now, one thing we do need to talk about here is they want to know the wavelength, and we know what the frequency is because it's right here, but we don't know what the speed is yet, and that means we've got 2 unknowns in the problem, and you can't solve it if you've got 2 unknowns. So we need to talk about what the speed is. Alright, this is light that we're talking about here, and in fact anything in the electromagnetic spectrum is going to move at the speed of light. Perhaps you've heard of that before. In Einstein's equation, E equals mc squared, the c stands for the speed of light. Alright, so c gets its own, or actually the speed of light gets its own variable c. And that's going to be 3.00 times 10 to the 8th meters per second. Okay, and so since this is a speed here, that's the same thing as v. So in this case, v equals c, which equals 3.00 times 10 to the 8th meters per second. Alright, so we can just plug our numbers in now. We're going to put in the speed of light since we're talking about light. Okay. And we're going to put in the frequency that they gave us up in the problem. And then we'll just do our division. And we come up with 2.5 times 10 to the negative 7th meters, because meters is the unit for wavelength right here. Okay, let me move that back over. Alright, so now we need to make sure that we're doing correct sig figs. We've got 2 sig figs in our given, we've got 2 sig figs down here, so that is our final answer. That one's correct. Okay, let's do one more of those and then we'll move on. Okay, here's the next question. An X-ray has a wavelength of 1.5 times 10 to the negative 10th meters. Find the frequency of this light. Okay, so we're going to write down our equation again. The speed of the wave is equal to the frequency times the wavelength. Alright, this time they want to know what the frequency is, so we circle the thing we want and leave it alone. And then we're going to undo what's happening to it. And right now it's being multiplied by the wavelength. So we are going to divide by the wavelength on both sides of the equal sign. Those cancel out. And so The new formula is frequency equals velocity over wavelength. Okay, X-rays. X-rays are part of this electromagnetic spectrum. Okay, here they are right here, and all of these move at the speed of light, like I said a minute ago. So the speed here is going to be the same as it was just a minute ago, 3.00 times 10 to the 8th meters per second. And then the wavelength is the one they give us up here in the problem, 1.54 times 10 to the negative 10th meters. And since we're solving for frequency, our unit should be hertz. Quick review of our scientific notation stuff. Remember, guys, I want you to be able to kind of predict what the calculator is going to tell you before you do it. Okay, so right here, we remember that if you're dividing scientific notation, you can divide the numbers in front, and then you subtract the exponents, and that will give you the answer. Well, you should be able to recognize that 1.5 is exactly half of 3. So it's a little bit more than half here, but if you were to divide this by this 3 by a half, you should get something close to 2, okay? And then 8 minus negative 10 is the same as 8 plus 10, so we should get something around 18 as our exponent. So I'm predicting, before I even type in my calculator, I should be getting something close to 2 times 10 to the 18th, alright? Now when we type in our calculator, we actually come up with 1.9480519 times 10 to the 18th hertz. Okay, well, obviously the 1.9 is about 2, so I agree with this. I feel comfortable that the calculator told me the right answer. You really need to get in the habit of doing that, because so many times you just believe whatever the calculator tells you, and a lot of times that will give you, that might be wrong. You maybe hit a stray button or something, and so if you didn't expect something before and you just trust the calculator, you won't know if it's telling you garbage or not, okay? Alright, now let's take care of sig figs. We have 3 sig figs up here in the problem, so we need 3 sig figs in our answer. And so our final answer then is going to be 1.95 times 10 to the 18th hertz. Okay? Good. So hopefully that's enough practice for you here on these two. You'll be given a worksheet in class that will give you more practice over this, and it's just going to be the same thing. You write the formula, you rearrange it to solve for something every single time. Okay, let's talk about the photoelectric effect here. Okay, the photoelectric effect is when a metal atom shines, or it emits light, it glows, and the reason for that a lot of times is because it's hot. So you'll see here that this metal is emitting light because it's got so much extra energy from being heated up. Okay, what's happening is that energy is coming in and striking one of the atoms, and then the electrons are jumping up to an excited state, is what we call it, and I'll show you that in just a second. And then when the electron falls back down to a ground state, or loses its excitement, it emits a photon of light and it comes back out. Okay? So we're going to leave it there for now, and I hope you'll join me in the next video where we will talk more about this photoelectric effect. As always, thank you for learning with me, and I'll see you next time.